Okay, so hi everyone. So welcome to our weekly. Wow, terrible! I see myself multiple times. Welcome to our. Wait, sorry, that's awful.
I will wait.
Thanks. Let's restart again. Okay, thanks. So, hi everybody. So today for our weekly seminar, we have the pleasure to have Janssen with us. Michael is also visiting us this week. He's working with a SMILE group. So he's in the visitor office. So everyone who wants to pass by and chat with Michael he will be here till Friday. So let me introduce him briefly. Michael graduated and obtained his PhD at the Radboud University in Nijmegen in the Netherlands. During the PhD, Michael developed a data reduction and synthetic data generation pipeline called the RPCard pipeline, which is dedicated to calibrate event horizon data using the CASA software. And as part of the EHT collaboration, Michael also led a study on the jet launching and collimation in the radio galaxy Centaurus A, which was published in Nature in 2021. After the PhD, Michael moved to Bonn instead to join the VLBI group of the Max Planck Institute for Radio Astronomy. And finally, last October, he moved back to the Radboud University to start as both assistant professor and project scientist for the African Millimeter Telescope in Namibia. That is something new that I hope we will hear a little bit about. So thanks for being here. The floor is yours.
I will unmute, and also I will turn on my audio so I can hear people if they have questions. I guess you also will have a look at the chat if someone raises hands. Okay, yes, thank you for the introduction. Yeah, I'm very happy to be here to work on the SMART project. And this is a little talk about, let's say, maybe some news. It's mostly VLBI news, right? So the talk is the title is a bit generic, but the extreme angular resolution, of course, when you see something like this, what I will be talking about, I should do it, put point here. So you see something like this, right? What I will be talking about is mostly very long baseline interferometry observations. You're probably familiar with it. So we coupled together different radio telescopes across the Earth to get like a supersized telescope that will give us this super high resolution. And also from my own background, the talk, it will be very much biased towards VLBI in the millimeter regime. So you see it here from the EHT. So there will be a lot of EHT science, maybe EHT news regarding what we can observe with the telescope. Also next to these two, very well-known famous sources where we can resolve the shadow of the black hole. Also talk about a little bit of what else we can do with the EHT. Yes, the bottom is always a little bit cut off. I hope there's something out that's. Sorry for that. So this is an introduction about what the EHT is. Most of you are familiar with it. So you have the array over here. Actually, the array in mostly its current configuration. So the first results that were published with the subset of these telescopes. So they were with the around 30 meter in Spain, LMT in Mexico, SMT in Arizona, 2 telescopes in Hawaii, 2 telescopes in Chile, 1 telescope in South Pole. And by now, so since we've published our first results, new stations have joined the array. One is the Noema interferometer in the French Alps. Another one is another telescope in Arizona, the Kitt Peak telescope over here. And the Greenland telescope has also joined the array. So what we're doing, and what I should mention, we mentioned it already, there are future plans to upgrade the array even further, and one that I will be talking about a little bit in the end because I'm heavily involved in it, is the Africa Millimeter Telescope. So you can see there's this obvious gap in the coverage of telescopes where if you put something here, get a nice addition to the overall UV coverage in this interferometer, and also the weather down there in Namibia which is very dry, not a lot of rain, is very good to do. Millimeter VLBI, which, as you know, I hope the Event Horizon Telescope is currently the array in which we can observe at the highest frequency, so at 230 gigahertz, to do VLBI from the ground. The equivalent is 1 millimeter wavelength. And the main science scale, what we're looking at, are now these environments immediately surrounding supermassive black holes, which you have in the center. You have an accretion flow around it. It launches these powerful jets when you have radio loud sources like M87. Sagittarius star may or not have, so galactic center may or may not have a jet. And what we're seeing is then at those wavelengths is a synchrotron emission that's emitted by this hot plasma from either the jet or actually both from the jet and the accretion flow in the immediate vicinity of the black hole. So that emission here is due to the gravity of supermassive black hole in the center is being lensed, so you get this lensed bright emission ring surrounding this central dark spot, which is a so-called shadow cast by the black hole, which is a direct consequence of the fact that the black hole has an event horizon. So due to this lensing at the event horizon, you get this characteristic shape of this circle with the dark spot in the center, which we're then interested in studying in, for example, testing general relativity. And as a note, that I find interesting in history, actually already in 1916, so the same year that the first solution to general relativity was found by Karl Schwarzschild, a solution for the Schwarzschild metric of a non-rotating black hole. And back then they didn't know that this mathematical solution corresponds to something like an astrophysical object like a black hole, but already the same year in 1916, David Hilbert in one of his lectures already calculated what, given this metric, the solution to general relativity, what would such an object actually look like. So he computed the light rays, the geodesics, as you show here, different impact parameters of what's happening with these light rays when they are trapped in the gravity well of the black hole. They may if we get too close, they may end up in the event horizon. Otherwise, you can light rays that circle, let's say, once or twice before escaping again, which is then essentially the original prediction of what we have seen here, actually, with observations that were done 100 years later. And the underlying principle, I guess, need little explanation is interferometry, because when you have the normal angular resolution of a single dish telescope is not good enough to be able to resolve these shadows cast by black holes, because the biggest one on the sky for those black holes where we know that they are radio loud, that they're actually emitting enough radiation that we can see them. They may also be bigger black holes, but they may be radio quiet, so we don't really see them. There on the sky have a size of about 20 to 50 micro arc seconds, so you cannot do this with a single telescope. You need to do interferometry, where we have an interferometer, you measure the radio waves, and you essentially measure with these spatial scales, so depending on the distance of your telescopes, you measure different Fourier components of the source. So two telescopes close to each other, you measure the large-scale emission of the source. Telescopes far from each other, you get the high resolution. So wavelengths divided by the distance of the telescope, and you measure the Fourier components that correspond to the small-scale structure of the source. And this has been done, before the EHT. There are many VLBI arrays, as the EVN, for example, European VLBI array. What's special about the EHT is that it observes at very short wavelengths, so it pushes essentially the limit of what we can do from the ground. So currently 230 gigahertz is really at the limit before it becomes impossible, because the phases are too unstable and the signals are too strongly absorbed by the troposphere of the Earth. But at 230 gigahertz is kind of the edge of where it's possible. And at that these high frequencies, you then get the required short wavelengths, so we have enough resolution. And to reach this 20 to 50 micro arc second, roughly this limit. But what's also important is the astrophysics here, because with just the resolution is not enough. You also need to see the source. If I go back here, to see it here, it needs to be in an optically thin regime. So if we were to look at it with a VLBI array that, let's say, has the required resolution but looks at centimeter wavelength, because it's synchrotron emission, all of this here, because emitted by very energetic particles, would be synchrotron self-absorbed. So it would be optically thick, and you would just see, this outer wall, essentially, wall of emission from the accretion flow and the jet that you cannot peer through. But we're actually quite lucky that, as it turns out, those two black holes, which we know are bright enough and are the biggest ones on the sky, it turns out that their parameters in terms of black hole mass and accretion flow are just such that they are optically thin at 230 gigahertz. So we're lucky with this experiment actually in three ways. So one is that those black holes exist and are big enough. The second one is that they're optically thin at this 230 gigahertz frequency. And the third one is that, this 230 gigahertz is really at the edge of what we can do. So it could have also been unlucky that this M87 black hole, it's very massive and far away, or the Sagittarius star in the center of our own galaxy had some different parameters, that they would be synchrotron self-absorbed at 230 gigahertz, and then the experiment would have not been successful. But we were lucky, we were able to do it. And the main science results, I think, that we got from the EHT is just that, what we look at here, those two, this image, M87 and Sagittarius star, there's this very simple characteristic ring shape, which is exactly as predicted by general relativity. So we have, in a plot like this, to check what's actually here is a function of gravitational potential, it's a function of curvature, the different GR tests in this post-Newtonian parameter expansion, so details are not that important, but you can plot here different types of tests that we can do for GR. So solar system objects over here, pulsars here, the stellar mass gravitational waves. And then we have a new unique range where we can test GR with the EHT in this range of supermassive black holes. So that's really the unique thing of it. Is there a question?
What is curvature? The y-axis in this black?
The curvature?
Defined.
It's the curvature, it's in GR, the curvature of space-time. I don't know off the top of my head the exact definition, but essentially, if you have the closer you are to a lot of mass that's in a very small region, the stronger the curvature is. So essentially, the curvature is what essentially causes the effect of gravity here. So if you have stellar mass black holes, they have, on average, a very high density. They have a mass of a few solar masses, but the event horizon is also very small. So if you're just outside of the event horizon, you have a very strong gravitational field with a lot of curvature. These supermassive black holes, 10 to the 6, 10 to the 9 solar masses, they're extremely big, actually. So the event horizon is very big. So the average density is comparable to that of water. So that is why the potential, I think here, because a lot of mass is very high, but the curvature here is much lower because because the gravitational pull is much weaker than compared to stellar mass black holes. Right. So so this is like the parameter regime of GR that we're testing, but because of also limitations, what we're really at the edge of what we can see, and the image is a little bit blurry, so it's difficult to exactly estimate how big is the size of this shadow cast by the black hole. For example, we are not there where we can really do precision tests of GR. So we can say, no, it's consistent with general relativity. But for M87, because we don't know the mass and distance all that well, that is all we can say. But for Sagittarius star, we have, due to these measurements of the stellar orbits by the UCLA and gravity groups, we know very accurately what is the mass and distance of this central object. So we can use it as a prior to get very accurate prediction of how big this shadow size should be. And with that, we can turn it roughly into tests of GR where you can say it's consistent with Kerr to within 10%. So there we can actually test some small deviations from general relativity, so from the Kerr metric of rotating black hole, cannot be larger than 10%. In this case for Sagittarius star. For M87, it's very difficult to say because it could also be that there are deviations, but at the same time our mass or distance estimate could be wrong. So it's degenerate. The size of this shadow is degenerate with the mass and distance estimate. So the size of this shadow is determined by the mass, the distance, and possible deviations from Kerr, and we cannot disentangle them. So that's why we can actually only do this really precision GR test with Sagittarius star. But we also need to understand the underlying astrophysics to be able to do this, because the emission is very messy. We do not see just effects of GR. We also see effects of the accretion flow, the jet, and so on. So to try and to understand this, we look at these type of general relativistic magneto-hydrodynamic models. So we simulate essentially our supermassive black hole systems just in a numerical simulation where we put a plasma flow around the black hole, which naturally forms some kind of rotation disk. We initialize it with some weak magnetic fields. So you see magnetic field lines here, which are then, when you have a rotating black hole, become wound up like a corkscrew structure by the frame dragging of the black hole. And by that, these jets are self-consistently launched in these simulations. And then we can ray trace them to compute from our simulation what type of radiation are we getting. And the parameters that enter these simulations are, for example, the spin of the black hole, the configuration of this magnetic field. There are essentially two distinct classes. One is called sane, which is a standard and normal evolution. So they have relatively weak magnetic fields. And the other one is MAD, which stands for the magnetically arrested disk. So there you have a lot of magnetic flux that starts to pile up right near the event horizon over here. And it then erupts all in one go in a very violent eruption and produces very strong jets. So that's roughly the difference between those classes. And with those parameters, we get a library of simulations. It looks roughly like this. So these are some snapshots of our models and what they actually predict in terms of the emission produced here in total intensity by the synchrotron emission surrounding the black hole. And now getting to some of the newer results. This is one that we've published last week, actually, which is that we've measured for the first time the signature of circular polarization on horizon scales in our measurements of M87. So it's a very difficult measurement actually to make because of the nature of how the instrument is set up. You can ask me about it later. But essentially here you can see the signature where we need to look into the difference in our two measured polarizations. So this RR and LL, that's you have your interferometer, your baseline, and you measure RCP at both stations, and you measure LCP at both stations. You can measure them simultaneously. You can correlate them, and then you can look at the difference in phase on a triangle of telescopes to get these so-called closure phases. Details are not important. These are closure phases, meaning that you have some measurable quantity that's relatively robust against gain errors. So if your telescope is slightly miscalibrated, those measurements are relatively robust to them. And this difference between RR and LL, that is signature of intrinsic or presence of circular polarization in the observations. And you can see here, it's very noisy, but on average, we have here a measurement that is non-zero, so we have an indication of presence of circular polarization. And what we typically do in the EHT, we have different methods to try to study this and try to reconstruct then an image from this data. And in this image, we also reconstruct all four Stokes parameters. And in this case, reconstructing the Stokes V, so the circular polarization. And you can see here, we have measurements on different days, so April 5 and April 11, this from 2017, and different frequency bands. So we have these are low and high bands. These are both 2 gigahertz wide bands. They are centered around 228 gigahertz. And you can see that if we use different image reconstruction softwares, they don't really agree with each other, and also you get different results on different days. And also sometimes here, for example, image reconstruction, but diffmap, differences between the different frequency bands. So it's very difficult to try to make a robust statement here. But I was actually involved in this other paper here that we published together, led by Frick Rudolphs, that tries to do this not with an image reconstruction, but with a simple geometric ring model to try to model this. Because if you have a simpler model, they have much less degrees of freedom than a full image reconstruction. You can get more robust results if you're in a noisy regime, but of course you put in a lot of prior assumptions that the source exactly looks like this ring model. But if we do this with this model, this is the last column here, we get actually very consistent results between bands and between days, and also we try different calibration methods, calibrating our data in different ways, and we always get this asymmetric structure over here, what seems to be in my view, we have detected a circular polarization signal here, but it's rather model dependent on the simple model. And we can also, what we also did is we looked at different synthetic data tests, so you can simulate an observation, put in a known ground truth Stokes V structure, see what our different methods are reconstructing, and you can see this new method, this is called so-called M-ring model, is, I think, it's not perfect, but it's doing a decent job of getting this asymmetry compared to the other methods. So I think that shows that in this case, this method is actually quite robust. Yeah.
What kind of polarization would you expect theoretically from the
That's the next slide. So
okay.
So those were the observations. And now the question is, what do the simulations tell us? And actually, circular polarization there you get mostly from Faraday conversion. So intrinsically, synchrotron produces mostly linear. Mm-hmm. If you have a lot of material in front, you can get this birefringence and Faraday conversion, and that predicts for every simulation some kind of circular polarization measurement. And you can see it's cut off here at the bottom. Well, we have two measurements. This one is a large-scale circular polarization. It was measured by ARMA. Because ARMA joins the EHT, we always get also the ARMA data for free in our observations. So we have the range over here, and these are the possible ranges predicted by the simulations. And in here, what we did is we took, because the methods don't agree with each other that well, so we just took a conservative upper limit of 4% circular polarization, where none of the methods they're all below 4%, so we can take that roughly as a limit, and then we can see where it cuts into our different models. And what you can see, this tail over here, those are mostly those sane models. Prograde, retrograde, that means it's the co-rotating or counter-rotating spin of the black hole with respect to the accretion flow. So we can start with this, ruling out some methods here, but it's not really, because just an upper limit, as you can see, most models are still consistent with this conservative upper limit. But if we take this, and also together with that we published 2 years ago, the linear polarization image of the source, where you get a clear signal, we can put in all the combined constraints, and we can see here those are the models that are still passing, and as you see, most of them are the MAD models. So we cannot really distinguish between different spins. That's all the data is not good enough for that, but we can broadly say that in these type of models with the same and MAD magnetic field configurations, and see in these models that MAD is strongly favored over the same configuration, and we really have this strong dynamically important magnetic fields. Then moving away a little bit from this horizon scale science, I'm going to talk a little bit about other things that you can also do with the EHT. And one thing is you can search for pulsars. You don't do this with the VOBI data, but you leverage the fact that we have some very powerful individual telescopes in the array, like ARMA or like the LMT, large millimeter telescope in Mexico, which is a 50-meter dish observing a millimeter wavelengths, and we record those single dish data essentially at the same time as our VBI data. So we can use it when we look at Sagittarius star to search for pulsars in the galactic center, because they're not that many. I think only 3 or something are known that are relatively close to Sagittarius star, but there are a lot of young and old stars, so we do expect that there is some kind of hidden pulsar population over there. And of course, the idea is that we want to find a pulsar in a very narrow orbit around Sagittarius star, because then you can do very accurate timing tests of general relativity by studying how the arrival times of the pulsars change when the pulsar is far away, it's on elliptical orbit, when it's far away from Sagittarius star, and when it gets close deeper into the gravitational well. And it's shown here, it's actually very complementary tests compared to the tests for GR that we can do with the EHT shadow. So long story short, so we searched for it and we didn't find any new pulsars. So the tricky thing is, of course, that at millimeter wavelength, pulsars are very weak, but we tried it anyways because we don't have the problem of scattering anymore. So galactic center is very difficult to search for pulsars because millimeter wavelengths, the pulsars are weak, but at longer wavelengths, the pulsars are very strongly scatter broadened. So they're really broad and it's difficult to find individual pulsars then. And we simulated what we think roughly could be a possible pulsar population in the galactic center by assuming that it has essentially the same characteristics as the pulsar population in the entire galaxy, which is just, we don't know what we search for, was an assumption. If that is the case, we can see that our sensitivity limits here, this is for the, actually back then LNT was just 30 meter, not a 50 meter, the ERA 30 meter telescope and ARMA, that we kind of understand why we didn't find any new pulsars, because we're just at the edge of a possible pulsar distribution. So we need to have more sensitivity and repeat this experiment. And one last thing is the planned wideband frequency update, bandwidth update for ARMA, where ARMA will get, I think, double or 4 times the amount of bandwidth, and which you can observe at the moment. So with something like this, you can bring down your sensitivity limit, and you will hopefully be able to find some new pulsars in the galactic center for maybe future precision GR tests. Then as I mentioned before, the only 2 black holes that are big enough to really resolve horizon scales are Sagittarius star and MPIfR, but the EHT is a VBI array. You can also observe any other radio loud AGN source. And what you typically see then is this innermost jet launching region over here, where the jet is magnetically dominated. And here's some results of that. We had here's an image of VBI at 1 millimeter of NRO 530. Here is one that's quite interesting. This is of J1924-29114. So yes, another source where this is the EHT image. So you can see the jet going in this direction, and you compare it to other VBI images at longer wavelengths. So each image here is you looking at the source on larger scales. So you see in small scales, the jet is looking in this direction, and on larger scales, it's actually bending like this. So in this source, you have the jet is being launched. You see it at the smaller scales, and then at some point, it starts to bend in this direction, maybe due to the presence of ambient medium. So it's quite interesting. We also looked at the very well-known radio galaxy Centaurus A, where the nice thing is that with ATCA and the Parkes radio telescopes, you can see the large-scale structure, these radio lobes produced by the jets and source on scales of millions of light years. You can zoom in with VBI observations prior to the EHT. This image here of the source scales of light years. And with the EHT, you can zoom in this core, and actually I think get a 16 times better resolution than is possible here, and really look like what this jet looks like on very, very small scales of less than a light day in the immediate vicinity of where it's being launched. You see this very characteristic, interesting edge brightening, so only the outer edges of the jet appear to be bright. We're still trying to understand how we can get extreme edge brightening like this. You can get it, for example, when you have a very thin hollow jet, like a cylindrical hollow jet. If you then look at it through projection, you will see more intensity at the edges compared to the center. That's one possible explanation. But overall, it's, I think, a very nice study because you can go on the same source from scales of resolution is half a light day to millions of light years. So you get a very complete picture of what the jet is doing across all different kinds of scales. And
What
here,
is the black hole in
probably here, because we think this is the jet that's the
the
approaching
one
jet.
is the counter?
This is the counter jet, so somewhere here. What we actually estimated is that here, one of these things where the synchrotron opacity becomes important, where if you were to resolve this at 230 gigahertz, you would still just see the jet, because here this whole region is optically thick. Here is where it turns over. In this region here, this would be the radio core. This part is optically thin at 230 gigahertz, and all of this is optically thick. And based on that, we estimated that if you want to resolve this, if you have enough resolution, you need to be looking at much higher at terahertz frequencies to be able to peer through the jet and be an optically thin regime. And two more examples. One is also the laser 3C279, where we got also, I think, done study by Jay and Kim. Very interesting result where you see here this interesting structure where it's very unusual, where this bright radio core is elongated in a direction that is perpendicular to the overall jet direction. So you just see these two blobs, but this blob is strangely elongated like this. So it could be signature of an accretion disk, or it could be that you have a jet that is being launched with a very wide opening angle like this, and then recollimates into the jet funnel over here. So jet being launched like this, recollimating over here, which is something that we think, for example, this might be happening in 3C84. And then for the future, we're still analyzing this data, but we also have measurements on OJ287, which is a very interesting candidate because it is possibly, due to periodicities in the light curve, a binary black hole candidate. So very interesting to look at this on these extreme VLBI scales. Now coming to why I'm here, but also to give you some idea of, in this EHT we develop a lot of methods and new things to do this tricky millimeter VLBI business. So we're kind of also improving on previous VLBI methods, and now some examples of how we can use them for other studies. And one is this project by Carolina to look for millilenses in a survey of flux limited sample of VLBI AGN observations, just to get the statistics of the number of millilenses to see if we can distinguish between different models of dark matter. And here I'm working with Avinash to use this RPCard pipeline that we use to calibrate EHT data with an automated pipeline. So it's very well suitable for a large-scale project where we use data from 5,000 sources like this. Then one other example where we used this same pipeline and got some improvement compared to previous standard VLBI methods is this paper that has been accepted now, so it should be out relatively soon. Those are the first GMVA observations of BLAC, where the phase Neumann, which you mentioned, is also joining the EHT, the sensitive array in Europe, is joining for the first time with all, I think, 15 stations. In the past that joined as Plateau de Bulle with just 6 stations. And now in 2021 joined for the first time with the full array. And then we looked at this data, and we show that it makes actually a very big impact in this GMVA array, which, by the way, for those of you who don't know the GMVA, it's a VLBI array similar to the EHT, but it observes at 3 millimeter and has more stations than the EHT. But it's actually now here in the GMVA, this is a plot of signal to noise ratio, function baseline length, by far the most sensitive station there. So a very sensitive new station in the array. And we used this and also this new RPCard calibration method to image BLAC in a single epoch. I'm getting this interesting image and showing a very interesting helical jet structure here. And it's very difficult to see, but in this comparison, this is the phases, actually functional baseline lengths using the standard manual calibration methods versus just using the pipeline. You can see due to all the tunings that the pipeline is doing, you get a much better phase coherence and therefore a better image. And we can compare this actually to a study earlier done by Carolina to see, with these new methods and this new instrument, how much better we can get the amount of improvement that we get in image reconstruction compared to previous studies. So here, previously from your paper, these were all single epochs, and you can compare, see some structure, but you see the average structure looks like this. And now you can compare previously what you get as an average structure when stacking many, many epochs to the amount of improvement that you now get with this updated array, updated methods from just using a single epoch, which I actually find quite impressive. Actually, how much time do I have?
Something like 5-10 minutes max.
Okay. Maybe I will skip. Let's see. I'll talk about this, and then I'll skip one part, and then get to the talk a little bit about the AMT at the end. So this one, so what I showed previously was a data reduction pipeline. Now, one thing that's also developed heavily, or driven heavily by the EHT, is the development of new VLBI imaging algorithms. One is this resolve algorithm, which is a Bayesian imaging algorithm, which has, actually how I see it, two big advantages. One is that you get actually uncertainties in your image. So in the end, you do not get just one single image reconstruction, but you get a full set of posteriors of possible images that fit your data. And the other one is, which might actually also be some for very good data sets where you might get some lenses to really get to the bottom of the uncertainties in the image reconstruction, is that with Bayesian methods like this, you also get, when you do this amplitude and phase self-calibration of the antennas in your VLBI array, so a very uncertain thing where things can go wrong. But if you do it in a Bayesian way, you also get nicely, this is as a function of time of the experiment here, you can nicely track the time-dependent uncertainties of your self-calibration gains for every antenna. So in the end, you get, and you fold that into your image posterior, so you really understand which features in this image can I trust and which ones can I not trust. And in traditional clean-based image algorithm, where you assume the sky is made out of point sources, you always put in usually your nominal telescope beam, and in some cases you can get some super resolution. So you can get some features resolved that are smaller than your longest baseline length in the array, if you have enough signal-to-noise ratio. But getting this super resolution and how much you get is always a tricky business, and has to be, there are some formulas you can use, but it's not really exact. So you can probably get some super resolution in this region here, but you don't know how much. The advantage of your posterior images, you can simply get the average image of all the possibles from drawing from your posterior, and in the average image you naturally get something which I see as some adaptive super resolution. So where you have the image structure where it varies a lot between different posterior images, like in this outer region of the jet over here, you get some diffuse emission, so you have some lower resolution. But the bright features, we have a lot of signal-to-noise ratio, and they always look the same in every possible image. You get very sharp image here, and naturally get in this kind of in this core this super resolution compared to the clean reconstruction. Maybe I will skip. So I had just to briefly mention this. There's also a very nice result published by Fuentes et al. Nature Astronomy. Was the result, when you talk about extreme resolutions, you also want to go beyond what you can do on the ground. So in the VLBI on the ground, the longest baseline you can get is limited by the size of the Earth. So you can get much higher resolution when you use space-based telescopes that are on baseline length that are multiple times the diameter of the Earth. And something like that, it's radio Astron mission, for example, you get 12 microarcsecond resolution, so even better than the 20 microarcseconds that we get with the EHT. And recently this very nice paper published again, 3C279, it was the EHT image that I talked about earlier, but with radio astronomy you see much more of the extended jet because it's a longer wavelength. You see this interesting helical filamentary structure over here, where they proposed this model where essentially individual components in the jet that travel along this helical structure. As they do that, they change the Doppler factor with respect to the line of sight, when the emission coming towards us, moving away from us, coming towards us again over here. That can explain the radio variability in this type of laser sources. But radio astronomy, actually, the mission has died. So one thing that people are looking into right now to do next is to do millimeter space VLBI. So we have something that we can connect to the EHT, and with that, you get sufficient resolution that you don't just see in the vicinity from the black hole, not just the ring itself, but you can resolve fine structure in this ring. And you may, if you're at very long baseline length over here, you see these n=1, n=2 structures. So these are the rings produced by photons that go once or twice or three times around the black hole and produce these narrower rings over here. It's very hard to see, but it's even thinner than over here, and then they go on like this. So very long baselines, you can start to do something like this. And with these rings, you can then, because they depend primarily only on the spin of the black hole, you can really do this precision GR tests, and you can see also black hole shadows in many more than two sources. On the ground, we can only do two sources. If you're in space VLBI, you can go also to high frequencies. There's no more troposphere. You can resolve the shadows of more, of a larger sample. And one, for example, would of course be we want to do this if possible. We can go to very high frequencies, seeing it in Centaurus A. And I had something on, you can ask me about it later, using AI methods to do some feature extraction. So as you saw previously, we have our models. It's difficult to compare them to the data. We can only rule out certain parameter regions. But the idea is that we use this library of GMHD models to produce a library of synthetic observations, train a neural network on it, and then let that neural network help us in figuring out, which models are best described by our data. But I will skip that in the interest of time, and instead talk a little bit about the Africa Millimeter Telescope. So if you remember from the first slide, the idea is that we put a new millimeter dish, actually the first millimeter dish in Africa, in Namibia because it's an ideal location. And the plan is to do it on this Gamsberg over here, which is a height of 2,400 meters, where we hope to be able to put a 15-meter class dish. Hopefully a design similar to the one from the Noema dish produced by IRAM. And from the current project, where we have funding for roughly 30 million euros, the plan is to have first flight in 2028. Let's see if we get there. And what we really want to strive for in this dish, because it's not the biggest millimeter dish, is to have very wide bandwidth recording of hopefully 16 gigahertz dual polarization, and to put multi-frequency receivers on there so we can simultaneously observe at 3, at 1, and maybe even at 45 gigahertz, so at 0.9 millimeter, and then expand on the current EHT science, where we have these static images of both Sagittarius star and M87 with an array expansion, and in the future with more antennas, we hopefully get enough coverage that we can do movies of both sources. So for Sagittarius star, getting a movie within one observing night, so within a few hours, and for M87, we would do movies by repeatedly observing over the year, so every month, for example. And next to VLBI, the science case will also be to do transient follow-up, because we won't have like a wide field of view. We just have a single pixel receiver in single dish mode. But if there are some transients out there, like gamma ray bursts or tidal disruption events, the idea is that we have an observatory that works mostly remote. And when it's not doing VLBI, so it can be triggered by transient alert, move there and quickly get some millimeter data of the transient. Because at the moment there are not that many millimeter wavelength telescope that can really do this. Particularly in Namibia, you have the advantage of being in the southern hemisphere, so you can see all that is happening in the galactic center very well. And you can do also very long monitoring of Sagittarius star and other AGN sources. And this last part, which is cut off, but it's very relevant to the people working here. Of course, the transient science will be a lot of synergy with the Argos project. We can maybe get a trigger from Argos and then follow up. And this monitoring of AGN here also in dual polarization. I think there's also a lot of synergy with the optical polarization monitoring from RoboPol. So here, some examples of what I said. Sagittarius star, for example. This is from the ALMA light curve during EHT observation. This is the flux of this compact component, so it's embedded in this mini spiral. The mini spiral is mostly constant, but the central component is really flickering all the time due to this complex accretion environment of the black hole. So the idea with such a telescope that can essentially always see Sagittarius star, we can do a very, very long monitoring of what's happening to the light curve to better understand the accretion parameters of Sagittarius star and maybe understand why it doesn't have a powerful jet. One other very interesting example, if you think again about the fact that we can see the galactic plane very well, where there are a lot of X-ray binaries. There was an example study done by Alexander Tetarenko, was that if you look at millimeters, so this was done with JCMT and SMA, even for a few hours, when X-ray binary is doing something interesting, in this case, actually launching multiple jet components in a very short time, you have a lot of structure in the millimeter light curves compared to here, these lower frequency light curves. So the millimeter regime is really, again, ideal to study the transient phenomena of X-ray binaries to understand how they are launching jets. I think in this time range, within 5 hours, there were actually 8, when they modeled this, they found 8 distinct jet ejection events from this source. So quite interesting. One other, I think by now well-known example are the reverse shocks or gamma ray bursts and their reverse shocks, which actually initially, if you were able to be on source, ideally within minutes, maybe a few tenths of minutes after the gamma ray burst has gone off, you get a lot of very bright millimeter emission from this reverse shock. So that's shown over here. Here, function of time. The emission of this gamma ray burst, so if you go to higher and higher frequency, shorter and shorter after the burst, the source is actually very, very bright. So this proposed sensitivity of the AMT, to see that for those sources, they're again an ideal target to be very quickly there at millimeter wavelengths to understand the jet properties of these gamma ray bursts. Then talking again about VLBI and making movies, this was also the reason why Africa is a very good place to put a new telescope, because you can roughly divide this array, this EHT array, let's say an eastern array, which would be, let's say this would be the eastern array, the telescopes over here, and a western array with the telescopes over here. So just to get an idea of what we can do with the AMT, because there was a PhD student at Radboud University, Noemi Labella, she has looked at, if you have an array like this, and you're looking at Sagittarius star, which is varying actually over a minute time scale, can you get an image reconstruction by just using this eastern part of the array, which sees the source first and rotates, and then the western part of the array. So you did the simulation, this was the model. If you just have the eastern part of the array without the AMT, you cannot get, with this limited baseline coverage, any good data out of it, so you cannot reconstruct a model of the source. So if the source at this part of the observing time in VLBI is doing anything interesting, you won't be able, like having a flare or something, you won't be able to see it because you cannot reconstruct an image. But if you add the AMT in its early time of the observation, with the E-center, you can see the source, you can get already a very good reconstruction that is also really showing how the AMT will be able to make an impact when you try to make a movie of Sagittarius star. And you can also see if you have the full final average reconstruction of such a movie with this underlying model, and you add the AMT, you can see you get nicely this crescent-shaped structure over here. The AMT, you're nicely able to reconstruct it. Without it, you kind of lose this, you get something that is not as close to the actual ground truth model as with the AMT. So it's not just for enabling movies, but also improving the overall image reconstruction of the entire array. This is the last slide. This is also an ongoing project that I think is very important to do also outreach in Namibia, because the idea is, if you put a telescope there, you also need people to operate it. You need think of in terms, the next generation of scientists and engineers who can take care of the instrument, use it, contribute to VLBI and EHD science and transient science and so on, and hopefully, build the next generation of instruments. And one thing that was initiated by RATPA that seems to be very, very successful is this mobile planetarium here that is used to now go all over Namibia to all the different schools, and it now has more than visited, been very well received. So more than 9,000 school children have now been in this planetarium, and they're always very excited and ask questions. So we hope, that we'll be able to, with that, we'll be able to get the next, generation of scientists and engineers from Namibia. And next to that, we also have bachelor, master, and PhD fellowships to further boost the science in Namibia and our collaboration. And with that, I'd like to end. Happy to take questions. Thank you.
Thank you very much for your nice talk. Any question here? Yeah.
Hi, thank you. I had a question about the resolve algorithm. That naively, I would not believe any structure smaller than the beam. So how can you really go super resolution and believe that it's there?
That's, maybe also a little bit of a philosophical question. So maybe the easiest answer of how you can trust this is by doing, again, synthetic observations. So you can simply put a model, and I did this for a result where you start putting in structure that is smaller than your nominal beam. It's not that this beam, this lambda over d, is a super exact limit. It's just a rough estimate of which Fourier components you measure. So with synthetic data, you can actually test and see that it actually works and does resolve structure smaller than. Really, it's just a nominal beam. The equivalent in clean is that when you have a clean reconstruction, what you do is you put point sources, which by definition have infinite resolution, and you can see in clean reconstructions also here that you get some, you can call it not random scattered structure, but coherent structure where the algorithm puts your clean components or your delta components that are on a coherent structure smaller than the beam. There is a paper, I don't know from which year, by Andrei Lobanov. This is explained in some for the clean algorithm, where this is explained in some more detail of how you get super resolution. But I don't know the details there. I just know that we can get it from synthetic data.
Let's take a question also from Professor Kilafis here. Number one.
Okay. I am sorry that I missed the first part of your talk because I had a class and the students delayed me with questions. So my question, I say all that because you may have discussed it. For the ring, the picture that we have is a two-dimensional picture, and we want to infer from that the three-dimensional structure of the emitting plasma. How safely can we make this this conversion from 2D to 3D?
Yeah, it's a good question. I think we only see the integrated emission, you know, which also, so if you're optically thin, you can integrate along it and you get the additional emission. So we never actually fit really a three-dimensional structure. When we compare the observations with our models, what we always compare is just, you know, the two-dimensional projection. So along every line of sight, essentially the integrated Stokes I, Q, U, and V, so the integrated Stokes parameters.
Okay, so then you must have an idea of what the emitting matter, what the geometry of the emitting matter is, create a model, and then compare the model to the picture with the observations.
Right. Yeah. What all of these models have in common is that they belong to the class of low luminosity AGN. So they are all this type of radiatively inefficient accretion flow. So that's an assumption which is certainly true for Sagittarius star because the accretion rate is 10 to the minus 9 or something Eddington rate, whereas for M87 it's 10 to the minus 7 or 6. So for M87, actually, that assumption is getting a little bit trickier, but for Sagittarius star, it's certainly true. And in this model, you have just this geometrically thick, optically thin accretion flow, this puffed up torus around the black hole. And in our models, these numerical simulations, you naturally get that by simply neglecting cooling. So it's also one assumption that we have. We don't have the effect of radiative cooling in those simulations because the radiative efficiency is so small. So due to this absence of radiative cooling, you have this very hot plasma that forms this puffed up disks.
Okay, thank you.
Eric? Yeah.
Yes. Oh, thank you for the very nice talk. I think you hinted at it in one of your slides. I just want to talk a little bit about that. You talked about also implementing multi-frequency receivers at the African Millimeter Telescope. This is very useful to do frequency phase transfer, right? Which is, it could be an alternative, for example, to doing space millimeter VLBI to get sort of rid of your atmospheric contributions. Like, what is the status of that? Like, how much has this been tested with the HDN?
Yeah, it's a whole nother talk. Yeah, we maybe a few points related to that in no particular order that I hope give you some better pictures. So we do want to have some system similar to what the KVN has. There's these 4 frequencies observing simultaneously. For most of our telescopes, maybe we can do 2. So the hope is that between what's now 86 and 230 gigahertz, that they observe simultaneously. We will need to tune the receivers a little bit differently to tune the LO so that we observe it's something that you get an integer ratio with 80, 82 and 256 or something like this. So that's possible, and that's the goal. We have tried to do some test observation. I think you had some test data at 3 millimeter, I think, if I recall correctly. Yibis, KVN.
Well, they're still pending.
Yeah,
A lot
so
of instrumental problems there.
So that's why I mentioned it, because we tried the same also, I think, for KVN too. Because KVN also, they have 230 gigahertz, and they're also joining the HT. So I think we've done this also with some telescopes, I think JCMT, SMA. I don't know exactly which stations they are, but it's also the same status. It's pending. So we have not really, we've done some test observation, but we need to analyze them to really figure out how it works. In terms of how far up we can go, it will help you to get fringes at, let's say, 345 gigahertz from 86 to 345, and it will extend the coherence time. But you still need to have after that enough signal to noise ratio that you get decent data. So if there's still too much, it cannot circumvent fully the atmosphere. That's what you still have. Sure. You still have the absorption. And by that, it cannot really be the same as, you cannot go to terahertz frequencies. There's the idea maybe we can do 690 from South Pole or ALMA in June, July, this winter there. But that really is, I think, currently pretty much the limit. After that, the troposphere, there's no signal coming through anymore.
Very interesting. Yes, question? No? Sorry.
Yeah.
Sorry, you are with your hand exactly behind
Okay.
Christina. So.
Okay. So this is maybe a dumb question, but I asked to other people giving a talk about event horizon and never got a straight answer. So what is that we are seeing in the event horizon images of M87 Sagittarius A? You said this is synchrotron emission.
Yes.
So I assume this is not accretion disk.
No, it's also this RIF. I maybe have some plot I can show you later from this. So it's not an optically thin disk. There you have much higher Bremsstrahlung. Bremsstrahlung maybe is a small contribution here, but that's for ADAP mostly at X-rays. So here really it is synchrotron, and it's coming also from the accretion disk. It's not entirely clear. It depends on which model you're looking at. How much of the emission is coming from the accretion disk and how much from the jet. There was one parameter which I skipped over, which is in our models we have to kind of paint the temperature of the electrons, because we in the GMHD models you study the dynamics of the heavier ions. You do not. There are some codes that can do like 2 fluid simulation that you can include also electrons. For most models, only the ions, and then when you do the ray tracing, you have to assume something for the distribution function of the electrons. So essentially say they have a fixed temperature ratio with respect to the ions. And there you have a free parameter of how hot are the electrons in the disk versus the jet.
Yes.
And that's one parameter that is not well constrained. So it's difficult to say, how much radiation is coming from the jet. How much from
when
the
we
disk.
study the accretion disk, we always assume that there's an emission that is black body emission. No?
Not these ones.
Temperatures.
Yeah, not these ones, because they are very optical. They're so. What's the opposite of dense? There's so sparse. So few particles. The density is so low that the thermal emission is essentially negligible. It's mostly synchrotron.
So those are radially inefficient accretion flows.
Yes. Yeah.
And in this case, the accretion disk emits mainly by synchrotron. That's what you're saying.
At this wavelengths, yes.
Okay.
Yeah.
Okay.
One other thing is also there's a paper from Jordi Davila, I think from 2019. I think it was actually about a non-thermal jet, so when you have accelerated particles. And in that paper, there's an appendix, and in that appendix, they look at the emission you get from the counterjet. Where it actually turns out that in their model, because the emission from the counterjet, because behind, it's strongly lensed, actually a lot of this emission is also coming from the counterjet. So it's, but from our model space, we cannot say. It's some combination of both.
So it could be a combination of a radiatively inefficient disk, or the jet base, or the counterjet.
Exactly. Yeah.
Yeah.
Okay, good. So thank you again, Michael.